Good morning, Prof. I am Felysse Chua, and today I'll be presenting on my FYP project, the ILP-based routing algorithm design for optical network on chip. This presentation is split into 5 parts. I'll bring you through some background, the problem I am trying to solve, the tools used, the solution developed, and finally, the evaluation of my developed solution. First, we will start with some background on the ONOC. Optical network on chip is increasingly used as an improved alternative for traditional interconnects in multi-core systems. Optical transmission improves on delay time, power consumption, and provides a higher bandwidth, all of which are common in electrical network on chip limitations. The architecture of the optical network on chip consists of 2 overlap networks, an electrical control network and an optical transmission network. The optical transmission network is used for bulk message transmission. The electronic control network is used for the control of the optical transmission network. The optical router is an important component of the optical network on chip, and its function is to provide the optical path between source and destination. In an optical router, there are 2 basic elements, the micro-ring resonator and the waveguide. The switch of the MR is controlled according to whether the frequency of the signal matches resonant frequency of the MR. When the MR is turned on, the signal gets coupled to the respective MR. The signal is delivered into the drop port, changing the direction of the signal. Otherwise, the optical signal continues in its original direction to the through port. Next, we will further explore the problem to be solved. The first problem commonly faced by the optical network on chip is communication contention. The optical circuit switching mechanism is commonly used. The optical path is first reserved by the electronic control unit when the path setup packet is sent by the source through the electronic network to the destination. This path setup packet reserves the optical path and configures the optical routers. After the path setup packet arrives at the destination, an ACK is sent to the source to inform it that the path has been established. And then, the optical layer begins payload transmission. When there is contention in the path setup process, the electronic network buffers the block message until the requested wavelength is available. Optical channels that have been reserved by the path setup packet on upstream links will be unavailable during buffering time. The setup process suffers from severe congestion under heavy loads, causing low utilization and high delays. The same problems are faced when the network is expanded over a large size and traffic is transmitted over longer transmission paths. In comparison, electronic circuits which use packet switching are less sensitive to contention since packets can be stored in situ. The second problem is the thermal susceptibility of the optical network on chip. Micro-ring resonators found in optical routers are highly susceptible to thermal fluctuations. Chip temperature can fluctuate both spatially and temporally and can vary by more than 30 degrees Celsius across a steady-state chip under typical operating conditions. As the number of cores on the chip increases, the on-chip gradient temperature could be even higher. The linear relationship between temperature and resonant wavelength can be expressed in the equation on the left. Due to the thermal optic effect, the resonant wavelength of the MR red shifts with increasing temperature and blue shifts with decreasing ones. Experiments show that the micro-ring resonators shift the resonant wavelength about 50 picometers per degree Celsius. This undesired mismatch between signal wavelength and the resonant wavelength of the MR will result in additional optical power loss, which potentially causes performance degradation and even functional failures. Now, we will go through the tools I have used. Linear programming is an optimization technique for a system of linear constraints. The objective function defines the quantity to be optimized. The goal of linear programming is to find the value of the variables that minimize or maximize the objective function. The model was implemented on the AMPL IDE with the CPLEX solver. For evaluation, a Python implementation with libraries like NetworkX, Pandas, and NumPy were used to manipulate the data. In general, the efficiency of the algorithm is important, but linear programming produces optimal results. The results obtained from linear programming can be used as a benchmark for how good a heuristic performs. Making use of the tools I have just introduced, two solutions were implemented: the multi-commodity flow model and thermal-aware task scheduling. The multi-commodity flow model is a network flow model where different commodities share common arc capacities. The model imposes capacities on arcs instead of nodes, and this capacity restricts the total flow of commodities on that arc. The objective function of the model is to minimize total cost for flow of commodities without exceeding arc capacity. Routing for inter-processor communication can be abstracted into a multi-commodity flow model. The objective function of the model would be to reduce the total cost for the flow of data from node to node. To minimize contention, the capacity of each link is only given 1 unit of flow, so there will only be one signal at any given time across the same link. The node requesting data will be the node where there is a demand, and the node that is sending data would then be the supply. By allocating costs to the links, the signal can be routed along a thermally reliable path. As previously mentioned, microring resonators are highly susceptible to temperature fluctuations, so there is a need to maintain a fixed temperature around each MR. A current is applied to a heater which generates heat, which is used to tune the surrounding temperature of the MR. In conjunction with the heater, a PID controller is used for thermal tuning. Temperature data is collected from a thermal sensor integrated with the core, and the corresponding current is generated for the heater. The control signal for the PID controller is given by the equation on the slide. Using thermal tuning between the source and destination nodes, the temperatures of the nodes can be corrected to the initial temperatures to ensure thermal reliability. The cost of the links between arcs will be the amount of energy in units for thermal tuning to achieve the desired temperature. This is given by the equation on the slide. Since request is related to the need for inter-processor communication, different time periods are also assigned in the ILP model. Here are the variables used in the model for optical network on-chip routing. There's a set of edges, nodes, and commodities in the network, and a set of periods for data transfer. Costs are assigned for each unit of flow on the edge, and a binary variable indicates if there is a flow on an edge from node to node in a certain time period. The capacity for edges between nodes is also indicated. The commodity number is allocated arbitrarily, indicating 1 for processor 1, 2 for processor 2, and so on. The input of the model is given by the demand requested for a certain commodity by a specific processor during a given time period. The output of the model is then the routing path for the transfer of data for inter-processor communication. The objective function of the model is to minimize total cost, which is given by the sum of the cost of all flows in the network. The constraint for communication contention ensures that only one communication signal is transmitted at a given time for a given path. For the multi-commodity flow model, this constraint is given by the capacity constraint on the edges. Since there is only one signal at any given time on the links, the capacity is kept at 1. Flow has to be conserved in the multi-commodity flow model. There should be data supplied to the nodes requesting data, and the nodes supplying data should be able to at least meet the demand. For intermediate or transshipment nodes, net flow should be 0. The ILP model is able to generate the lowest cost path for the optical network on chip while avoiding contention for different time periods. Here are two examples of routing for a 3x3 optical network on chip. For period 5, there is a request of data from node 3 to node 7 and a request of data from node 7 to node 3. The first request takes the path from node 3 to 6 to 9 to 8, then to 7. The second request takes the path from node 7 to 4 to 5 to 2, then node 3. For period 10, there are three separate requests from node 3 to node 7 to node 9, and node 9 to node 3. The paths taken can be seen on the slide. In this way, the ILP model is optimized to reduce contention while providing a thermally reliable path. Thermal-aware task scheduling has been used at the software level for multi-core systems to obtain optimal schedules for the assignment of tasks to cores. For higher throughput, embedded system applications such as multimedia applications are usually modeled as task graphs, and the interdependence among tasks can be further exploited to improve the thermal efficiency. For the optical network on chip, power dissipation from processing tasks increases thermal variation, which affects thermal reliability of MR signals. By developing a thermal-aware task scheduling ILP solution, it can minimize the thermal variation among MRs and improve performance of the application. Here are the variables for the thermal-aware task scheduling model. There is a set of tasks from the task graph and a set of processes for the mapping of tasks. A binary variable indicates if a task is mapped to a processor, and another variable indicates the processor to which the task is assigned. A binary variable indicates if a task finishes before another to maintain task precedence. Another binary variable is true if a task I is executed on a processor number lower than task j. The start times, latencies, and energy consumed by the task are also used. There are also variables for accumulated heat generated in the processor, cost of assigning a task to a processor, and the completion time of the application. The input of the model would then be the task graph with its latencies and energy consumed for each task. The output of the model is the assignment of tasks to processors, their individual start times, and the completion time of the application. The objective function of the model is to minimize the total heat accumulated by each processor and optimize the total execution time. In the equation for the cost, alpha is the tuning parameter. The first constraint ensures that each task is mapped to a processor and there is a single processor number for each mapped task. For the precedence constraint and task graph constraint, any task I that precedes task j, both tasks cannot be executing concurrently. Processing of tasks should be done according to task graph, and tasks can only be executed if the predecessor is done executing. The non-overlapping constraint ensures that only one task is mapped on one processor at any given time. The at least one position constraint ensures that all tasks are executed. The order of tasks ensures that for any two tasks with interdependency, either task I should execute before task j or vice versa. There should only be one task mapped on one processor at any given time. The order of mapping ensures that task I is either mapped to a processor of a lower number than task j or vice versa. The last constraint for accumulated heat takes into account the heat generated by each processor and the heat dissipated from the environment. After implementation in AMPL, tasks are distributed more evenly to reduce power dissipation for each processor to reduce thermal variation. In the table, you can see the assignment of tasks from a sample task graph to different processors and their individual start times. Now, I will show you a demonstration of the two ILP models on the AMPL IDE. This is the task graph and the multi-commodity flow model that I'll be using. The AMPR IDE was used for the implementation of my ILP models. The CPLEX solver was used to solve them. In the first part, I will map the task to processes, and this stage aims to produce thermal-aware scheduling and an improvement in overall performance. So here you can see the implementation and the data file of the task graph, and the run file here is used to execute the model. So let me now run it, and here you can see the assignment of tasks to the different processes. You can also see their start times and the total execution time. So you can also see there's a relatively even distribution of tasks. This is to reduce the total power dissipated. So now we may look at the routing for the ONOC, and this model aims to minimize contention while giving a thermo-reliable path. Here the ILP model is implemented, and the data file here has all the relevant information such as the cost of the arcs. And the run file is used for the execution of the program. So now let me run this model. And here you can see the links that I use at different time periods. So for example, at period 35, there is a flow of data from node 9 to node 3. So it uses the link 9 to 6 and 6 to 3. It also has the cost, which is the amount of energy used for thermal tuning to ensure a thermo-reliable path. You can also see here at the same time period, period 10, there are different requests and different paths are taken to prevent contention. Now, let's move on to evaluate our models. We will first evaluate the optical network-on-chip routing model, then the thermal-aware task scheduling model, and then evaluate both models as a whole. For the first model of optical network-on-chip routing, the developed ILP model is evaluated against a popular greedy algorithm, Dijkstra's algorithm. Dijkstra's algorithm is able to obtain the shortest path from source to destination efficiently. After repeated tests, Dijkstra's obtain a lower cost for the multi-commodity flow model, but incurs conflicts since the same low-cost links are used when there are multiple communication signals transmitted in the same period. Even though the greedy algorithm produces a lower cost in terms of thermal tuning, energy used due to communication contention is an important contributing factor, especially as traffic increases. This leads to higher energy consumption than the ILP model. The developed ILP model is further evaluated with continuous mapping of a task graph and saw a 60.17% improvement of energy consumption over the greedy algorithm. The second model of thermal-aware task scheduling, it was evaluated against continuous mapping, which is commonly used for the mapping of tasks to processes. The Python library NetworkX was used for the creation of the task graph. The Pandas and NumPy libraries were used for the manipulation of data. Working with a 2.4 GHz processor, the ILP model achieves a more even distribution of tasks among processes compared to continuous mapping. This can be seen by the graph on the left. Now, let's look at both models as a whole. Task graphs are mapped to processes, and then based on communication patterns between different processes, a path is obtained by the routing algorithm. Repeated tests are run, and the average results are obtained to produce the two graphs on the slide. In the mapping of processes, total power dissipated by all processes remains constant, since processes are operating at the same frequency. However, the ILP model developed aims to reduce thermal variation and improve throughput performance. Looking at the graph on the left, there's a more even distribution of tasks for the ILP map model than for continuous mapping. This reduces total power dissipated for each processor and helps to ensure thermal reliability of the optical network on chip. Now, looking at the graph on the right, we compare the energy consumed by the whole model. The ILP model produced an overall average improvement of 43.6% in terms of energy consumption. In general, improvement is much more pronounced when there is more inter-processor communication, since this increases likelihood of communication contention. This is an important concern under heavy loads or when networks are of a larger size. In conclusion, two models were developed, one for routing and the second for thermal-aware task scheduling. These two solutions minimize communication contention and maintain thermal reliability of the optical network on chip. However, ILP is an NP-hard solution and does not scale well when tasks grow exponentially. Hence, to further the work done, the model can be used as a benchmark of other heuristics since ILP produces optimal solutions. Thank you.